Hi class, it's me, Mr. Morris, and today we're talking about the gas laws. These laws are related in terms of equations, and we're going to go through a few equations and a few example problems, and then we're going to go deeper and combine all of them together and do a bunch of practice problems. So today we just kind of want to give a brief introduction to what the gas laws are. The first one we want to talk about is Boyle's law. Now Boyle's law is talked about when we have a flexible container or a piston. In other words, the volume is allowed to change. Because Boyle's law is the relationship between pressure and volume. You could see that on this graph on the right hand side, that I've got pressure and I have volume. Those are the two things that we're showing the relationship to. And as volume increases going from left to right, the pressure is decreasing. So you can see that the volume of the container, as the volume is increased, the pressure decreases, and if the volume of the container decreases, the pressure increases. It's an inverse relationship. We can explain the reason for this in terms of the kinetic molecular theory. If you increase the volume, gas molecules have to go farther before they collide with the walls. And remember, collisions are directly proportional to the pressure. They collide with the container walls less often because of that. So the gas pressure will decrease because there are fewer collisions. The collisions are less frequent. When the volume is decreased, there's less space for these molecules to move around. The gas molecules have a shorter distance to travel before they collide with the container walls, so they collide more often, and that makes the pressure go up. That's the idea of Boyle's law. And the relationship is shown by this equation, P1V1 equals P2V2, where P1V1, that's the initial or starting pressure and volume, and P2V2 is the final pressure and volume. This is an inverse relationship. It means that as one quantity goes up, the other one has to go down, and vice versa. The amount of gas in moles and the temperature have to be constant. And it's important that you recognize that the pressure units, P1 and P2, have to match. The units have to match. And the units of V1 must match the units of V2. We've got a couple examples here that you may be familiar with. If you've ever gone on a drive in the mountains, or if you've ever gone up in an airplane and you had potato chips with you, the bag expands because at higher altitudes, the air pressure is lower. So if you decrease the pressure, the volume will increase. You could also think about a piston. Maybe you would think about an air compressor, a bike pump or something. If you were to close off the other end of the pump, you could feel the pressure as you depressed the plunger into the piston or into the bike pump. So the pressure inside a piston increases as the plunger is depressed to decrease the volume. Those are a couple real-life examples of Boyle's law. Now here's a question that would be a word problem that we could solve using Boyle's law. So we can see that the volume in this problem is changing. I have volume given, and I have a second volume given. Okay, it changed to this volume. I also have a pressure given, and I'm wanting to know what the new pressure is. So we could recognize that this is V1, this is P1. This final pressure that I'm looking for is P2, this is V2. Now it's a good habit to label these out on the side, and this is going to help you get ready for physics as well. So we're going to go ahead and spend a little time doing that. So I have V1, P1, V2, P2, and we want to label each of them and check our units to make sure that they are appropriate. I have 5.00 liters, and then P1 is 1.08 atmospheres. V2 is 10.0 liters as given in the problem, and P2, that's what I don't know, so I'm just going to put a question mark there. Well, the liters, those units match, the volume units match, so my pressure units are going to match. I'm going to have atmospheres as my unit in the answer. Now let's see if we can solve it. Remember, our equation is P1 V1 equals P2 V2 from up here. We're just going to write it down. And then we're going to plug variables in. We're going to plug in those numbers. So P1 is 1.08. V1, that's 5.00 liters. So I'm multiplying 1.08 times 5.00. P2 is what I'm looking for. Since I don't know it, I'm just going to leave it as P2. I'm going to call it P2. And then V2 is 10.0 liters. So just 10.0 works. And then what we want to do is rearrange to solve for P2 just like we were solving for X. I'm going to divide both sides by 10.0. When I do that, that cancels out. And I could punch that in my calculator. 1.08 times 5.00 divided by 10.0. I'll find that P2 equals 0.540. And again, our units for pressure are atmospheres in this question. ATM, which stands for atmospheres. There's our answer. Okay, next thing that we could come across is Charles' law. Now this is also a flexible container or piston, but we're not talking about volume this time. Or we're talking about volume, we're not talking about pressure this time. We're talking about temperature. So if the temperature increases, the volume of the container will increase. If the temperature decreases, the volume of the container will decrease. This is our relationship is between volume and temperature, and it's a direct relationship. You can see that as the temperature increases, the volume is also increasing. This is why. When the temperature of a gas increases, the gas molecules move faster, they collide with the container walls more frequently and forcefully, and that really causes the internal pressure to increase. But because the container is flexible, that pressure on the inside pushes out on the walls of the container, and it increases the volume. This is if pressure is constant, but temperature changes, and volume is allowed to change because it's a stretchy container or a flexible container. This is called Charles's law. It's V1 over T1 equals V2 over T2. By the way, you do not need to memorize these laws. I'll show you why next class we're going to spend some time on it. And you do not need to memorize these laws. We just want to learn how to use them. This is a direct relationship. As one quantity increases in value, the other also increases, and vice versa. So if I increase the temperature, the volume increases. If I decrease the temperature, the volume decreases. Temperature, you've got to make sure that you understand this. Temperature has to be in Kelvin. So what that means is we're going to add 273 to our Celsius temperature in order to get kelvins. The amount of gas and the pressure is constant. Your volume units have to match. Couple real life examples. If you were to inflate a football inside and then take it outdoors on a winter day, it's going to shrink a little bit. It'll go flat. Another example in the opposite direction is when people fill up life rafts in tropical waters, they intentionally underinflate them just a little bit. And the reason is because when you take a life raft outside in the sunlight where it's nice and warm, it'll swell a little bit. And you don't want your life raft to pop. Okay, let's do an example of Charles' law, and then we're going to break between pages. Make another video after that. So we have volume and temperature. I have V1, T1, V2, and T2. Those are the variables of our equation. Now let's identify each one. I have 4.40 liters. Well, liters are volume. It's collected at 50.0 degrees Celsius. That seems to be a temperature. What will its volume be after we cool it to 25 degrees Celsius? Okay, so this sounds like it is temperature 2. This is volume 2. This is temperature 1 and volume 1. Now that we know what they are, we can label them and make sure we have the units we need. So V1 is 4.40 liters. T1 is 50.0 degrees Celsius. Remember, if you have Celsius, we always need to turn it into Kelvin. So we're going to add 273. V2 is what I'm looking for, and it should give me units of liters since I had units of liters as the other volume unit. All right, and then T2 is 25 degrees Celsius, which we'll add 273 to. All right, and 50.0 plus 273, if you put that in your calculator, you'll get 323 Kelvin. And if we add 25 plus 273, we get 298.0 Kelvin. Now we can plug in our numbers and solve, now that we have matching volume units and temperatures in Kelvin. So our equation again is V1 over T1 equals V2 over T2. We're going to be using cross multiplication to solve this for the most part. If you got another method that you like in algebra, that's acceptable. This is just one way that seems to be pretty easy for a lot of students. So let's do that. 4.40 liters over 323.0 Kelvin. V1 over T1 equals V2 over T2. I'm going to erase that K because it gets a little confusing when you put units in these equations. And V2 is what I'm looking for, over T2, which is 298.0 Kelvin. All right, and if I wanted to solve for this, I need to get V2 by itself. Right now I have V2 divided by 298. If I wanted to get rid of that 298, I would multiply on both sides. So multiply by 298.0 on both sides. Or you could cross multiply. Those are two different ways of thinking about the same thing that I'm doing right here. Either way, we do 298 times 4.40 divided by 323. V2 will equal 4.06 liters. All right, that's a look at Boyle's law and Charles' law.